All right, so another type of vector addition question that we have to go over are called, or what we call boat questions. They're going to be a bit of a relief because they're only perpendicular. Okay, you're going to have across the stream and down the stream as your two directions. Okay, so you're not going to have, you know, a bunch of angled things finding x's and y's and all of that stuff. So from the vector perspective, these questions are going to feel easier. Okay, they do involve some v equals d over t sometimes. Okay, also going to feel a bit easier. They still use some of the stuff we do about vectors, so that's why we include them here. All right. So a boat question is a vector analysis type of question involving two vectors that happen concurrently. Okay, all the vectors we've done up until now was one happened and then the other. Okay, if they happen at the same time, does that change what we do? It doesn't. Okay, it doesn't matter whether they happen one and then the other or they happen at the same time. They'll produce the same result. Okay, so I'll give you a bit of an example here. Okay, let me get Seth to help me here for a second with a little demo. It's super easy. All you're going to do is push the chair. Okay, so if I do this and I push the chair this way and then I push the chair that way, the end result is the chair ends up here, yes? Okay, this is the part I'm going to need your help with. I want you to stand over here. Okay, I'm going to push the chair that way. Seth's going to push the chair that way. Okay, ready? Put your hand on there. Okay, we're going to push at the same time. Go. The chair end up in the same place? Did we do the same thing? But we did. It doesn't matter whether I pushed it and then I pushed it, or we both pushed it at the same time. The forces were the same. It ended up over there, both times. Okay, so it doesn't matter whether the vectors happen one and then the other, or whether they happen at the same time. Okay. In a boat question, the vectors are happening at the same time, because a person is trying to row across the river while the river is carrying them downstream. Okay? In these type of questions, we're usually talking about velocity vectors, not displacement vectors. But all vector quantities are added the same way, so that part doesn't really matter that much. All right, so what I would like you to do is copy down what's on the screen right now. Boat questions, vector analysis, and then I'll scroll up so you can see the whole question, and I'll have you write down the whole question. All right, so before we even start like the math of a question like this, let's establish the mechanics of a question like this. If I'm on the shore of a river and I row my boat towards a spot on the other side, am I going to end up at that spot? What do you think? If I point the canoe straight across the river, where am I going to end up? Straight across the river? Where am I going to end up? Downstream. Actually, if you point your canoe directly perpendicular to the current, you're going to wind up in the river. Okay, but let's just say that that wouldn't happen. Okay, if I was actually rowing perpendicular to the current, okay, I wouldn't end up right across the river. I would end up downstream a ways. Okay, the only way I end up directly across the river is if I angle upstream and I row somewhat into the current, so the current pushes me back to straight across. Everybody follow me there? So there's two kinds of boat questions. Rowing across questions, where you ironically don't end up straight across the river, okay? And going across questions, where ironically you don't point straight across, but you end up straight across the river. Okay, so there's rowing across, where you end up downstream, and going across, where you aim upstream and end up right across. Okay, the first one we're going to deal with is a rowing across, so you're going to end up downstream. Okay, that's what the question says. All right, so to set up a boat question, we draw a picture, just like we always do. Okay, so if I have a river, so I'm just going to draw my river here. Okay, and the river is 200 meters wide. Okay, and this person is apparently an Olympic rower, okay, who can row at 3.5 meters per second, because that's fast to row a boat. Okay, 3.5 meters per second. They're rowing directly across. So that means what they're doing is this. rowing that direction 3.5 meters per second. While they are doing that, what is the river doing? What do rivers usually do? They flow. Which way do they flow? Downstream. Okay, so the river in this question is doing this. Flowing downstream at 1.2 meters per second. These two things are happening concurrently. That is, at the same time. So I draw them tail to head because they're both happening to the boat. Okay. The boat is going across and downstream at the same time. Okay. The result of that is that the boat does this. Okay. So imagine this. This is going on, and I put a drone in the air right above where this person is rowing. Which line am I going to see? What's the drone going to see? The drone is going to see the boat doing this. Because that's the sum of the two vectors acting on the boat, across and down. Okay. Everybody all right with that idea? If the person aimed upstream, okay, at an angle, the drone would see the person going straight across. Okay? It would see the canoe pointed like this, but it would see the canoe going straight across, despite what the person was doing. Okay. All right, so would this side still be the resultant, even though it's velocities instead of displacements? Is that still the resultant velocity? All the other diagrams we did, it was the resultant displacement because we added displacement vectors. Now we're adding velocity vectors. Can this still be the resultant velocity? Absolutely. It could be the resultant acceleration. It could be the resultant force. Just depends what two things you're adding together. Okay, so this will be my resultant velocity, and that will be its angle. It's just perpendicular vectors. We're going to do Pythagoras and one trig calculation, we're going to be done. This part of the question. Okay, so if I want to calculate that resultant velocity, okay, v is going to equal the square root of 1.2 squared plus 3.5 squared. Okay, so our resultant velocity is 3.7 meters per second. Okay, along this line, we have to find that angle. Okay, so 19 degrees. Okay, and that is going to be east of north. Okay, so what the person ends up doing is moving at 19 degrees east of north at 3.7 meters per second. Okay, so does that mean when they get to the other side, they're going to be downstream a little ways? Okay, with the information we have in this question, before I do it, see if you can calculate how far downstream they're going to end up. I will give you a little hint. This is 2 v equals d over t calculations. 2 of them. 2 v equals d over t calculations. So what I'm trying to find is how far downstream the boat ends up, that distance there. Okay. Can I use that resultant velocity I calculated, the 3.7 meters per second at 19 degrees east of north to do that? I can't. Why not? Right?
Because it's a vector.
Right, it's a vector that doesn't point in downstream, does it? It points 19 degrees east of north. That's slightly downstream and mostly across the stream. It isn't down the stream. Do I know how fast I'm going down the stream? It's the speed of the current. So if I'm trying to find D, how far downstream I end up, and I know V, how fast I'm going downstream, what am I missing? Time. Okay, so let's look at what else I know. I know it's 200 meters across the river. And I know I'm going across the river at 3.5 meters per second. Can I find time with those two numbers? Okay, is that the same amount of time I'd be going downstream? It is, because once I get to the other side, I will also be this far downstream, and I won't be going anymore, because my canoe will run into the shore on the other side, and I will cease to do both at that point. Okay? So I'm doing both for the same amount of time. As long as I'm going across the river, I'm also going down the river. Okay? The time is the same, because they happen concurrently. That's why I used that word before. Okay? Not only are they happening at the same time, they are happening for the same amount of time. Okay? Everyone all right with that? Okay. So I've got 200 meters. I know the distance, 200 meters across. I know how fast I'm going across, 3.5 meters per second. So T equals D divided by V, 200 divided by 3.5. Okay, so 200 divided by 3.5 says I got to row for almost a minute. 57 seconds before I get across. Now, the whole time I'm going across, I'm also going downstream at 1.2 meters per second. T, 57, times V, 1.2. I'll end up 69 meters downstream. Now, that kind of makes sense, right? I mean, I was going a lot faster across than I was downstream, so I should go further this direction than I go that direction. Okay? The reason we bring that up during vector addition is because that's how the last thing in this unit works as well. Projectile motion. When you throw something up in the air, it is both moving horizontally as well as vertically, and it's doing it at the same time. So we have to be able to do vectors that happen concurrently. That is, not only at the same time, but for the same amount of time. Okay? How many of you feel like your brain's going to turn to mush after today? Okay? That is okay. That is usually how people feel at this point in the unit. Okay? Generally, that goes away. Because either your brain turns to mush and you don't notice it's mush anymore, or because you just get it and stop turning to mush. Okay? All right. What do we got here? 310. You know what? Rather than do another boat question, I'm going to talk about what we're going to do tomorrow and Thursday. Okay, so tomorrow and Thursday, you're going to be working in groups of like 3, maybe 4, okay, people. And what you're going to be doing is I'm going to give you a map of a part of Jasper National Park. On that map, I'm going to mark 5 locations. Okay, starting location, and then some cabins you're going to go to, and then your final destination. Okay? What you and your group are going to have to do is you're going to have to A, plan a safe route to all of the destinations that don't involve jumping off of cliffs or drowning in rivers or any other manner of disaster that can happen in the mountains. So basically, I'll teach you how to read a map so that won't happen. Okay? Once you have your route determined, then you're going to do some measuring and some figuring with vectors and scalars. you'll measure how far you'd actually have to walk, okay, from one point to the next, because you won't be able to go in a straight line, it is after all mountains, okay? And then you'll do some vector analysis. If I could walk in a straight line, what would I have done? Okay, you'll do some B equals D over T stuff, okay, things like that. It's pretty straightforward, it's a lot easier than what we've been doing right now, but it still makes you do some X and Y stuff without having to draw a bunch of tail-to-head nightmare things that we've been doing for the last little while. Okay, so that'll be Wednesday and Thursday. That'll be the only class time you'll get for it, but it should be enough for you to be pretty close to done by the end of Thursday's class. Friday, we'll come back to this, and then you get a week off to try and demushify your brain, okay, before we come back to the vector stuff when we come back after the break. Okay, so that's the plan. So you can start thinking about who you might want to work with for this, okay, make sure everybody's included. If you have a group member who's going to be away on Thursday, okay, make sure you give them a job tomorrow, okay? Because you don't want them to get out of having to do work because they're not going to be here, okay? So if you have a group mate who's not going to be here Thursday, okay, you're going to want to assign them a job. After tomorrow, you'll know kind of what things you might assign them. There's 5 days, maybe you give them day 5, and they have to do all the work for day 5 while somebody else does day 4, whatever. You can be able to figure it out, okay? Now, your position versus timeline, remember that is due on Thursday, 8:30 a.m. through Google Classroom. I've had a few more people come in and have me look it over. You can still do that tomorrow if you want. Okay, we do have the altered bell schedule tomorrow, but I will still be here before school and after school if you want to pop in to have your stuff looked over, and of course lunch hour as well. I will be here for part of it because I have to supervise the first half of lunch tomorrow. All right, so that opportunity is there should you wish to take advantage of it. What was the other thing I was going to tell you? But there was something I was going to show you. And it has to do kind of with vectors.